Hi, welcome back to C23 Classroom channel. For today, I would like to discuss about solution for boundary layers that has laminar and turbulent boundary layers. So in this syllabus, we assume that we have a thin flat plate like this and a boundary layer occur on it. But the problem is in previous lesson, we calculate only 100% boundary layer or fully laminar boundary layer or fully turbulent boundary layer. But in this problem, we try to solve a situation where we have a part of laminar boundary layer occur before it turns into fully turbulent boundary layers. So let's say we have a problem like this. Estimate the boundary layer thickness at the end of a 4-meter long flat surface if the air free stream velocity is 5 meters per second. And also predict the drag force if the surface is 5 meters wide. We have two conditions here. First, we try to calculate by neglecting the laminar boundary layers, and we try to account the laminar boundary layers if the Reynolds critical is 5 times 10 by the power of 5. So in this case, the velocity profile for laminar and turbulent boundary layer is not given. To simplify this calculation, it is okay for us to take Blasius exact solution as representative for laminar boundary layer and 1/7 power law as representative for turbulent boundary layer. So we try to solve the first question, means we assume that the laminar boundary layer is not affected the result. So because we neglect the laminar boundary layers, what we should do is first we need to check whether the Reynolds number at the edge of the plate is exceeding laminar limits or not. So this is the Reynolds number equation, rho ux over mu. We substitute the value here, and so in this case I use ux and nu, which is this is the kinematic viscosity of air, and I get 1.25 times 10 by the power of 6. As mentioned in the question, Reynolds number critical is 5 times 10 by the power of 5, and what we get here is Reynolds number larger than the critical value, so means that the boundary layer is in turbulent condition. As I said in the previous slide, because it is there are no specific velocity profile in this case, so I took 1/7 power law as the velocity profile for turbulent boundary layer. So from the previous lesson, we get that delta is equal to 0.38x over Reynolds number by the power of 1 over 5. We substitute the value here according to the questions, and we could get 0.09917 meter. So according to the question, the length of flat plate is 4 meters. To calculate the drag force, this is the common equation for the drag force, CD 1 over 2 rho AU square, and we substitute the value of CD. So we could get this CD by doing the von Karman solution with 1/7 power law, which is the U over U is equal to Y over delta by the power of 1 over 7. We could get 0.073. So we already discussed about this in a previous lesson. After we substitute, we get 1.28 Newton. Now we go for second question. So in this calculation, we need to account the laminar boundary layer. So first, we need to calculate what is the boundary layer thickness delta. First, we need to know whether laminar boundary layer is long or short, because if laminar boundary layers is too small, might be we could neglect the laminar boundary layers. We need some confirmation on this. So we have a Reynolds critical as 5 times 10 by the power of 5, and we equalize this value with the Reynolds number equation, rho ux over mu or ux over nu, where nu here is the kinematic viscosity. So Reynolds critical numbers here means this is the location, this is the limit where 100% turbulent boundary layer occurs. So means that before this Reynolds number, we could assume that all calculation can be used as laminar boundary layer. So we complete this, we solve this equation, we could find that x is equal to 1.6 meter. It is mean that laminar boundary layers was occur for 1.6 meter from total plate length, which is 4 meters. It is 40% from the whole plate length, means that this value is too large and it cannot be neglected. It needs to be accounted in the calculation. So means that first you need to verify whether the laminar boundary layer need to be account or not. So first what we need to do is we take Blasius solution as the representative for the laminar boundary layers. From the Blasius solution, we could get that delta is equal to 5x over third Reynolds number. We substitute the value and we could get that the boundary layer thickness is 0.0113 meters. Then we do the reverse calculation here, which is that if delta is 0.0113, so we could substitute with the boundary layer thickness from the turbulent side, the boundary layer thickness from the 1/7 power law to get the value of x here. So we substitute the value of delta with 0.0113. We put the Reynolds number here, and then we could get that the x here is equal to 0.292 meters. So what it is mean by that calculation? So it's mean that for the first calculation, so we solve the laminar boundary layer here. So it create the laminar boundary layers occur until this point. So this length is 1.6 meters. So laminar boundary layer occurs until x is equal 1.6 meters. And then start from this point, the turbulent boundary layers start to grow. So however, as we learned previously, the turbulent boundary layers, the theory of turbulent boundary layers or theory for laminar boundary layers need to be start at x equal to 0. So means that we need to draw these turbulent boundary layers, and we cannot do our calculation from this point because this is not its starting point. We need to imagine that this turbulent boundary layer has its own starting point. So we need to know where is this turbulent boundary layer's starting point. So what we need to do is, we know that the laminar boundary layers create boundary layer thickness at here, and we could determine it by using the Blasius solution. So then we substitute the value of Reynolds critical here. This is the Reynolds critical point. So we substitute the Reynolds critical here to get the delta or the boundary layer thickness at this point. Okay, this point also share a sharing point of laminar and turbulence. So means that we could calculate what is the x here, the distance here, okay, the distance here, if we know the thickness. So from the laminar boundary layer thickness, we get it is around 0.0113 meter. So mean the thickness here is 0.0113 meters. So we substitute this thickness within turbulent boundary layer thickness equation, which is 0.38x Reynolds number 1/6. So in this term, we need to expand the Reynolds number because Reynolds number has rho ux over mu. So we have one x here, x by the power of 1/5, and we have another x here. So and then we need to solve. You need to solve this first. Okay. Then we substitute the value of delta here with 0.0113. So we could get the value of x. So according to this calculation, we could get that x is equal 0.292 meter. So what it is mean? So it means that from this point, so we need to extend the value of x here, 0.292 meter. So at this point, the turbulent boundary layer should be started. Okay, so in this calculation, we show that we mention this x equals 0.292 as x prime, mean the distance from the merging point between laminar boundary layers and turbulent boundary layers to the starting point of turbulent boundary layers, which is x prime, x dash here, so 0.292 meters. So we could say that the total distance that has turbulent boundary layers can be calculated by using this equation. So this means that we have a total length here. So and then we need to deduct minus with the length of laminar boundary layers. And then we need to add with the extension of this length, which is x prime. So we could say that the total length for turbulent boundary layers only, it is equal to total of the flat plate here minus with the xt, x laminar here, and then we add again with the value of x prime here. So according to what we have here, so we have 4 meter length, 4 meter long flat plate minus 1.6 the length of the laminar, and then we add 0.292 mean the extension of the boundary layers that occur inside the laminar boundary layers. So we get total 2.69 meter. So means that after this, we calculate everything by using equation of turbulent boundary layers. However, we just imagine we only need to consider flat plate length as 2.69 meter only. Okay, so it is because in laminar or turbulent theoretical calculation, we find that we develop our equation by using boundary condition, which is x is equal to 0 and delta is equal to 0. So means all the equation that we have now must be developed from its starting point. So, for example, when we agree to use that the length of turbulent boundary layer is 2.69 meters, so we calculate the Reynolds number, rho ux over mu, we substitute the value and we get it is around 800,000 value here. We substitute the value of delta 0.38x over Reynolds number by the power 1/5. So it's mean this equation we take from the 1/7 power law. Means that we assume that the velocity profile for turbulent boundary layer is y over delta by the power 1/7. So we get this value, we substitute with all the value that we have, we could say that the delta is 0.0668 meter. So what it mean? It means that So we just calculate the turbulent boundary layer here, and then because the length here is only 2.6 something, so we could determine the boundary layer thickness here. So when we compare with the previous calculation, we found that the previous calculation with totally neglect the existence of laminar boundary layers, the answer is quite different. It has 37% difference. The first calculation shows a higher value, 0.0917, while the second calculation is 0.0668. So according to the observation from the experimental work, if you could conduct it, we could find that the calculation by using this idea means accounted of laminar boundary layer is more accurate compared to the previous one. Now we need to calculate the drag force here. So we first we calculate the Reynolds number, and we must bear in mind that now we are calculating drag force for the total plate. So means that we need to calculate the Reynolds number for the total plate. So we need to use X here is 4 meter, not 2.6 something. We need to use 4 meter here, and we calculate, we get 1.25 times 10 by the power of 6. Then we need to use a special CD before we could calculate the drag force. Why we need to use special CD here, drag coefficient? Because we need to have a drag coefficient that included the influences of laminar and turbulent boundary layers. We cannot use just one CD that come from laminar or that come from turbulent boundary layers. Okay, please bear in mind, if you calculate boundary layers that have two parts, laminar and turbulent boundary layer, you need to use special drag coefficient like this, 0.073 over Reynolds number 1 over 5 minus 1700 Reynolds numbers. So we substitute the value of Reynolds numbers for the real length, for the real flat plate, and you will get it is around 0.00304. We substitute into this equation, so CD is 0.00304. We have rho density of air 1.164. We have an A 4 times 5, and the free stream velocity which is 5 meter per second, and then we get 0.0885 newtons. So how to determine this one? So it's need to be determined with an empirical method. So this is not a part of this syllabus, but what I could show you is this is the guideline to choose the value of CD. So it's depend on our critical Reynolds number. So if the critical Reynolds number is 3 times 10 by the power of 5, so we need to use this drag coefficient. And if 5 times 10 by the power of 5, so this is the CD for this one, and for 6 times 10 by the power of 5, so this is the official value of drag coefficient.